We are now going to look at another aspect of the kind of data manipulation that can be done with the C language, which is related to manipulating numbers as a set of bits, right. Now, this becomes useful to us especially for many kinds of embedded systems programming or operating systems programs, where we are actually interested in storing data at the levels of individual bits, right, and to check the values of individual bits, especially let us say that we are trying to communicate with the outside world. We might want to be able to read back a value and check whether, let us say, a particular switch has been turned on or a button is pressed, or whether we can turn on or off a given light based on specific values that we have. Now, C allows us to manipulate bits directly inside a number, right, and the operators that are available for that are what are called the bitwise operators, right. In particular, we have these four. The ampersand symbol is called the bitwise AND. You would remember that, if I put the double ampersand symbol, that's actually the AND operation for two condition clauses, right. If I am writing an if statement, I would have something if something and something else, that would be a double ampersand, right. So, that is basically the condition check, the AND operation between those. The single AND is, it is logically related, it is still trying to perform the same kind of operation, but it is now being done at the individual bit level, right. So, this is again something you have to be careful about, because if you use a single AND where you wanted to have a double AND, C is not going to complain. It will perform an operation, it will then decide on some truth value, but it may end up giving you something different from what you expect. In most cases it might even work correctly, but in some cases it may behave differently. Anyway, the single ampersand is what is called the bitwise AND operation. It allows you to take one bit, AND it with another bit, or more importantly take two numbers which could be 8 bits or 32 bits or any other data type size, and AND them all bit by bit, right. So, it sort of does a parallel AND operation between all the bits of two integers if necessary. Right. The pipe operator, the vertical bar, right, which you might see on top of the backslash character in your keyboard, would be the bitwise OR operator. It ORs two values together. There is also an exclusive OR, right. Exclusive OR basically says either A or B but not both are going to be true, right. True meaning the value 1 as opposed to the value 0, right. Remember that we are working at the bit level. So, when I XOR something, what I am saying is that these two bits are going to be considered. If both the bits are 0, the XOR of the result is also 0. If any one of the bits is, or rather if one is 0 and the other is 1, the result will become 1. If both are 1, the result will again become 0. Right. How do we use that? We will look at some examples later. There is also this thing called the bitwise NOT operation, which is not a binary operation. I mean, or rather it does not take two operands, it just takes a single operand and inverts all the bits, right. This is also called negation, right. It is basically the same idea as a ones complement. It basically flips all the bits of a given number or a given value. A related and very useful concept over here is the idea of a bit mask. Let us say that we have a number like this is just some random number that I have written down, and I want to check, right, what is the status of bit number 9. See, the numbers down here indicate the bit position from the least significant bit, which is typically called bit 0. Then I have bit 1, 2, 3 and so on, so that this one where I have the red box around it would be bit number 9. And I want some way to check whether bit number 9 is set or it is not set. Set meaning that it has the value 1, or cleared meaning it has the value 0. So, how do I check something like that, right? Because after all I have many other 1s and 0s. So, if I just try taking this number and comparing it to, let us say, 1, that is not going to work. If I try comparing it to another number which has exactly this number set to 1, that is also not going to work, because there are many other bits that are also set or unset over here, right. So, I need some way to isolate this bit alone and then check the resulting value. So, in order to isolate that, what we do is we create something called a bit mask. So, these green numbers out here essentially have zeros everywhere except at the place that I am interested in. So, this is called a bit mask. What I do is I take that bit mask and I write it in hexadecimal simply for convenience. I could have written it in binary, but there's like no good notation for binary numbers in C, right? I could have tried converting to decimal, but that's just confusing. It's not easy to interpret a decimal number in terms of its binary value. Hexadecimal is a lot easier that way. Why? Because I can just basically take chunks of 4 bits at a time and convert them to hex. So these bottom 4 are zeros, the next 4 are zeros, then I have a 0010, which basically is this value 2 out here, right. So I have straight away converted this big value that I have into this nice and compact 0200 in hexadecimal. What happens when I AND these two numbers together, that is I use this bitwise AND operation? What will happen is, if this bit was 1 and this bit is 1, the result over here will give me a 1 at exactly this location, right. In other words, if I AND these two together and I find that the result is non-zero, it basically means that this bit was set. If the result is 0, it means that this bit was 0, because all other bits have been eliminated from the computation by using this bit mask. Okay. I could do one thing further, which is by basically using another operator called the right shift operator, right. The shift operators are also in some sense bitwise operations. They are what are called logical operations, right. They are used in order to manipulate data at the bit level. I can right shift by a certain number of bits or left shift by a certain number of bits. In this case, if I take this result and right shift it by 9 bits, this 1 that I have out here will get shifted down into this location, the LSB. All other bits have already been eliminated because of this bit masking, right. So this kind of approach can be used in order to check the value of a given bit, or it can be used to toggle the value of a given bit, set a bit, or invert a value altogether, right. And let's look at some examples of that. So first things first, we are going to look at some just plain bit operations, right. I'm going to start off with an integer value out here and then show what happens if I was to just OR it with the value 0, 1, okay. So let's just clear the output here and run this code. And what I have done is I have used the notation %08b, right, and 08 basically means use at least 8 characters to represent the output, and use binary representation. In other words, take the number x and convert it to binary and represent it, okay. Now I should probably have given %32032b, right, and what that would do is actually use a 32-bit value to represent, because as you can see, when for certain values, you actually end up getting the higher order bits being set to 1, in which case, given that this is an int which is a 32-bit value, it actually uses 32 bits to represent the result, right. But let's go with this for now, right. What we have is, if I OR a 1 into it, I can see that my result basically has zeros everywhere because I initialized it with 0, except for a 1 at the LSB, the least significant bit. Why did that happen? Because I ORed 1 into it, okay. What happens if I OR the number 02? Now 02 in binary has the value 0010, okay. So I have already set the bottommost bit, I am also setting the next bit after it, and I find that both of them get set in the result. I get the result 1, 1. If I print this out in decimal, I will find that this value actually shows up as 3, okay. Now what happens if I take this and I AND it with 0, 1, right. Now effectively what this ANDing with 0, 1 is saying is that, get rid of any other bits in the higher order locations, make them all 0, and because this turned out to be 1, it remains as 1, okay. What about an XOR? Remember what an exclusive OR does. If a bit was already 1, it will make it 0, if a bit was already 0, it will make it 1, right. And we can basically run it through and find that the result of exclusive OR ends up giving us all zeros. And finally, what I can do is I can also just invert the bits. At this point in time, x actually has the value 0. If I invert it, all the bits in it are going to become 1. I am then also ORing it with 1. That's not really making any, it's not changing anything in any way, what ends up happening is the result basically shows up as all ones out here. Why is it printing so many ones? Because remember, it was declared as an int. Okay, if I had declared it as an unsigned char, it would probably look different. Okay, so this is just to sort of illustrate how the bit operations can be performed. Now let's look at a little bit more of how bit masks can be applied. In order to demonstrate how bit masks work, I have basically taken an integer and initialized it to some value in hexadecimal. And the reason I have chosen hexadecimal is because it sort of makes it easier for us to visualize the number. I could have written it in binary or in decimal, and nothing changes, because as far as the language itself is concerned, these are 4 bytes, that is all, right. It is only about how it shows it to us that changes. So what I am going to do is I am going to basically print a number of different things out here. In the first case, I am going to take out the bottommost bit of the value and show us what that result is going to be like. Then I am going to AND it with 0xFF, which should actually give us the bottom 2 nibbles, the bottom 2 4-bit values or of hex, or in other words the bottom byte. Okay. If I do FF00, then you can imagine that these 2 values, the C and A that we have out here, are going to be retained. Everything else is going to get set to 0. And similarly, I can see that if I go down to FF00, FF00, I should be able to mask out specific values within this entire range that I have out here, right. So let's quickly take a look at that before we comment out the rest of this. And if I run with that much, what I find is that the first one gives me just a 0, because it turns out that the bottommost bit of this value is actually a 0. But if I AND it with 0xFF, I get back the FE that I have out here at the LSB bits. If I do FF00, it gives me CA00. In other words, it has got rid of all the higher order bits, it does not even display them. It keeps the place corresponding to the FE, but it has made them 0 because they were ANDed out, right. And similarly, up to this FF00, FF00, at which point I get AB00, CA00 out here as the result. Okay. So all of these, in other words, are just AND operations that we have. Okay. What about the rest of it? If I look at this, for example, I can set individual bits in this, right. So for example, by ORing the value 0, 1, 0, 0, what I can basically say is this is bit number 4 actually, right, that is present over here, because what I am doing is it is the 5th bit from the right hand side, 0, 1, 2, 3 and then 4, right, is what I am sort of setting out here. And what I can see is I am going to print it out in binary, and when I print this result, I can see that down here the setting of the 5th bit 0, 1, 1, 1, it was already set to 1. It did not make a difference, the final result also remains the same. But when I ask it to set this other one, 1 followed by 3 zeros in hex, I find that there is one bit out here, right, that has actually changed, right. The middle bit out here has actually changed from 0 to 1. That was the one that got set by doing this OR operation out here. So in other words, if I want to forcibly set a particular value, I can do it in this way. But what if I just wanted to toggle it? If it was 1, I want to make it 0, if it was 0, I want to make it 1, easy enough, right, just use toggle, and what I can do is I can print, and that would basically show me that this value out here, right, this one that you can see, has essentially toggled, the bit in the middle has toggled from a 1 to a 0, right. I can also check a given value, which basically tells me whether or not a particular value is set, right. And in this case, when I ask it for bit number 10, right, which basically corresponds to 1, 0, 0 followed by 0. So basically there are 10 zeros following the 1, right. So this 4 corresponds to 0, 1, 0, 0 in hex. That is how I know that this is the 10th bit. It checks the value, it ANDs x with this particular number, and then it basically tells me either it is set or it is not set, right. and in this case it goes through, checks this particular value. I believe this is the 10th bit, right, over here, and it basically tells me that yeah, it's not set in this case, it is not equal to 1. Okay. And I can also just run this through in a loop and basically ask it to print out for each one of them whether the bit is set or not set. How do I do that? I basically take this value 0x01, left shift by how much? By I, by whatever it is that I wanted to actually, which bit I want to check, okay, and I use that in what's called this ternary operator that we have out here, right. Basically I check the value of set. If this is equal to 1, I don't print anything in this string out here. If it is equal to 0, I print the string not over here, right. And when I run this, it basically tells me that bit 0 is not set, bit 1 is set, right. You can go look at the numbers over here from right to left, right, and you will find that in fact bit 1 is set, bit 2 is set, etc. All of these are ones that you see, bit 7 is set, and so on, right. You can verify the result yourself. As an extension of this, I have also got another program over here that I would encourage you to just play around with, right, at some point, which what it does is it sort of tries to put all of these things together, right. It basically says that I can read data, I can put it in a loop which basically gets a character printed in from the standard input, right. So you can see that I basically run a getC from stdin. We know that the getC or fgetC basically allows us to get a character from a given stream, and when I say stdin over here, that is the standard input stream. As long as that input is not equal to q, I basically check certain values out here, and it allows me to either set or clear or toggle a given bit within a number, right. And if I run this, what I can see is it basically starts off by printing out the initial value of x all in binary, right. It prints it out as 032, right. So if there are no leading zeros, it puts zeros over there. It uses 32 bits in order to represent the number. What I am going to do is basically tell it to set, let's say, the 5th bit, and the result, as you can see over here, basically goes and sets the 5th bit. How does it do that? Remember, it basically takes the bit mask, shifts it into the correct position, performs an OR operation, okay. Now what happens if I wanted to clear that bit, right? If I say again the 5th bit and I want it to be cleared, it's gone away, but I have to be a little bit more clever about how I clear a bit, right? Think about it, I want only that particular bit to become 0. For example, if I had, let's say, the 2nd bit, then the 5th bit and the 8th bit all set to 1, but then I tell it to clear the 5th bit, only the 5th bit should become 0, right, and the other bits, that is the 8th bit and the 2nd bit, should remain as 1. In order to do that, what we do is we take this value 0x01, left shift it to the position that we want, invert that so that we get ones everywhere except in that particular position, and perform an AND operation, right. So this particular thing, ORing with a shifted mask and ORing with a shifted bit position and ANDing with a negated mask are very common, especially in embedded systems, as we will be seeing later, okay, not in this course. So this can be used for clearing. You could also use toggle, right, and I could straight away basically go and say, okay, toggle the 5th bit, and if I do the same thing again, it toggles it back to 0. How does it do that? That's even simpler, it just basically XORs with the value that you have shifted into the correct position, okay. So this can be used to sort of understand a little bit about how bit manipulation works. It can be quite useful in a lot of contexts. Now there is one last thing that I am just going to sort of talk about in passing over here. I am not really going to discuss it in a lot of detail. It turns out that you can also use what are called bit fields within structs in C, right. So if I declare a struct foo like this, where I have 4 unsigned integers a, b, c and d, but I specify that the colon 5 over here, effectively what it's saying is that a is a 5-bit number, b is also a 5-bit number, c is a 3-bit number, and d is a 3-bit number, okay. And I can basically assign values, x dot a is equal to 10, x dot c is equal to 10, and sort of see what happens as a result of doing this, right? And if I go ahead and run this, I basically find that A gets the value 10 which I assigned to it, C got a value 2. Now why did that happen? Because the number 10 is actually 1010 in binary, but C is only a 3-bit value. So it only got the bottom 3 bits 0, 1, 0, which has the value 2, right? So internally C has automatically taken care of ensuring that my data structure is using only the appropriate bits that I need. What is even more interesting is that if I had just declared these as unsigned ints, then each of these A, B, C and D would have used 4 bytes, and the total size of X or size of Y would have been 16 bytes, right? We can in fact see that that's the case by sort of changing this around, and let me just comment this out and get rid of this part out here. And if I run this, then what I find is that the size of X and size of Y actually show up as 16 bytes. And now you can also see that C came out to be the value 10, right? D was uninitialized, so I can't really guarantee what it turns out to be. It turns out that it just randomly picked up some other value out there, right? And the addresses, you can see that X and Y are basically 16 bytes apart. But if I go back to this declaration where I have the bit fields out here, right, and if I run this, then I find that A gets the value 10, C gets the value 2 because it's only a 3-bit value, X and Y take 4 bytes each, and their addresses are actually, well, not quite 4 bytes apart, they are a little bit more. So this is more to do with how exactly alignment of the different values happens internally. The other thing that might be a little confusing is, hey, this should have taken only 16 bits, which is 2 bytes, why did it take 4? And that, it turns out, is actually something more confusing about how C actually ends up packing data into bit structures, okay. The bottom line is, I introduce this over here primarily to sort of say that yes, this is a facility that is there in the C language, but I would strongly recommend against using it unless you are very clear about how exactly things get packed into the data structure and how the compiler is going to respond to it. As you can see, if you change these numbers around, you will find that at different sizes the number of bytes that are occupied by the resulting structure will change, right? And how exactly those change is not directly predictable just given the number of bits that you are using, or rather you can predict it if you know a little bit more about the compiler, but it does require some internal knowledge about how the compiler packs data. It is in general preferable to use the bit masking approach in order to handle individual bits that are present, and in some cases you might find that that ends up being a little bit more complicated, but it can always, over there you have perfect control over how to access each individual bit in a given data type. Whereas over here you are sort of relying on the compiler to do it for you. It should do it right, but it's potentially confusing to someone else who is reading the code later and trying to understand it. So my suggestion would be that this could probably be avoided unless there is a very specific reason to use it. I just wanted to show it for the sake of completeness.